In order to analyze the diffraction grating, we need to do a similar analysis to what we did for two-slit interference. But in this case, instead of just having two waves to think about, we actually have potentially hundreds of waves to think about. Now, obviously, we haven't included that in our entire picture. We have about 10 here. But again, keep in mind that even if your laser beam is only a millimeter wide, you probably have hundreds of slits that it's going through. So if you have all of these different waves adding up at a screen, if they have slightly a different phase when they get there, there are just so many added up that if you, for instance, have, a 5-degree phase difference from each one of these, that eventually you get back to zero. And so once you've added that whole circle up, and in section 5, which we're not going to talk about in depth, the book goes through this analysis for the single slit diffraction scenario. But basically, once you have these many waves adding up, even if just one to the next has a slight phase difference, that will cancel once you add up all of them. So an analogy might be if you're in a room of two people who are both talking, but they're saying different things, your brain might be able to process one or the other. But if you walk into a room where there are hundreds of people talking and there's not, one person standing right next to you, you're just going to hear noise. However, if all of those people were singing the same song, you would be able to hear what they're saying. So that's a rough analogy, but basically the idea is if we have perfectly constructive interference, we know that they're going to add up. So perfectly constructive interference between these first two, or say these two, if we know that that depends on the angle, so we get that magic path length difference here that leads to constructive interference, that we have constructive interference between these two, and then the next two, and so on. So in this case, we have perfectly constructive interference, right? They're singing the same song at the same time in the same key, then every single one adds up. So we're going to get a bright spot at that angle on our screen. For any other angle, you get just a little bit of destructive interference between these, but once you add all of these up, it's gone. It's completely destructive. And again, that mathematical analysis is a little more complicated, but some of that is explored in section 5. So to get that perfectly constructive interference, we know that this path length difference, delta r, needs to be an integer number of wavelengths, where that could be 0, 1, 2, so on for m. But then we also know that if we form our little triangle, that we have one part of the triangle which is d, and we have another part of the triangle which is our theta, and so d sine theta is what that path length difference actually is. So keep this in mind, that this is the analysis so far that you've seen that's been really similar to the two-slit interference. So that idea that there's an angle where you get constructive interference, that part of the analysis is completely the same. The difference is that we now are going to say that we fall off to zero very, very quickly. So the other thing, because of the spacing of our slits here, that we actually have much larger angles involved. So if we go to actually do out the analysis to get to position, when we did this for the two-slit interference, we could use the small angle approximation. We are not using the small angle approximation here. And our first one might be able to count. The first one might be at a small enough angle, but the second one typically isn't. That the angles we get here from a diffraction grating are big enough that you really don't want to use the small angle approximation. So notice that a lot of the analysis is the same, but mathematically we're not applying the small angle approximation. So we go from our angles at which we have our constructive interference to then changing that to position. Again, keeping it as sine of theta and keeping it as tangent of theta. And as you can imagine, you can find theta from this equation and then plug it in here. So do note that we can't just simplify this form beautifully because this is defined in terms of theta and we don't use the small angle approximation. So this doesn't simplify down as much. So the big difference here is that we get very, very sharp lines. For the two-slit interference, we didn't have as sharp of a fall off. It just kind of went sinusoidally, or as a cosine squared, between bright and dark. Now, at whatever angle we have a bright fringe, it doesn't go very far. We're not going to do the analysis of what the width of this fringe actually is, but the more closely spaced your slits are, or even the larger area you've illuminated, the sharper these get. So again, the reason that we don't just have kind of it go slowly to dark is that we effectively do have destructive interference in this entire region, considering the fact that we're maybe adding up hundreds of waves. So that's how we get to dark here. And again, notice here that we see that it's not evenly spaced. That is enough for you to know that we haven't used the small angle approximation. So once you use the small angle approximation, the equation will make it look as if it is evenly spaced, but mathematically that is not what happens, and it's not what we observe. Notice that there is always a bright fringe straight back. That is our m equals 0 case. And again, that's because that spot is an equal distance from every single slit. So m equals 0 we don't normally use as much, but then we're off at some angle for our m equals 1. Part of why diffraction gratings are so interesting and part of why we do scientifically use them is for spectroscopy. Because these fringes are so narrow, you actually can separate different colors of light. And if you have all wavelengths present, i.e. it's a continuous spectrum of light, then you just see a rainbow here. And again, that's where you see a rainbow from CDs or DVDs. You might see a rainbow when you look through those glasses. However, the rainbow itself isn't necessarily interesting. What we can do is basically do a calibration to know that maybe here on the screen you have 300 nanometers, and then maybe here on the screen you have 700 nanometers, and you would use known wavelengths to do that calibration. And then you actually can look at unknown sources and figure out what lines are there. So for instance, we can look at gas emissions from sodium or hydrogen, and that then you can measure what those wavelengths are and do some spectroscopy. For instance, looking at the hydrogen energy levels, as you might be familiar with. There's also ways of looking at, for instance, the solar spectrum and seeing that there are lines that are missing. That starts to tell you something else. So we're not actually going to talk about spectroscopy in this class, but especially if you've taken some chemistry or some astrophysics, you might be familiar with spectroscopy, and fundamentally that works from a diffraction grating. So most of our diffraction grating problems will have spectroscopy of one form or another as an application.